The database was fast in development. It was fast in staging. On the day of launch, under real load, writes slowed to a third of their expected speed. Nothing had changed. The constraints had always been there. There were just now 100,000 users writing data simultaneously, and each write was doing more work than anyone had measured. Constraints are not passive. They are not labels that sit alongside your data, describing what it should look like. Every constraint is an instruction the database executes on every write operation that touches the column or table it governs. A NOT NULL check runs on every insert and update. A check constraint evaluates its condition on every insert and update. A unique constraint queries an index on every insert and update to confirm no duplicate exists. A foreign key constraint, depending on the database engine, may query the reference table on every insert into the child table and on every delete from the parent. These are not occasional operations. They are guaranteed operations on every write for the lifetime of the constraint. Think about a customs checkpoint at a busy international port. Every container that passes through the port must be inspected, manifest checked, weight verified, contents declared. For a port processing 50 containers a day, the checkpoint is unobtrusive. The inspectors complete each container quickly, and the flow of goods is barely affected. Scale that port to 5,000 containers a day without adding inspection capacity, and the checkpoint becomes the bottleneck. The inspection process has not changed. The volume has, and the cost that was invisible at 50 containers is now the defining characteristic of the port's throughput. A database under light load hides constraint costs the same way. The work is always there. It only becomes visible when the volume arrives. In 2021, a Dutch SaaS platform launched a document management product. During development and staging, the team had tested with datasets of around 50,000 records. The production schema included a comprehensive constraint set, NOT NULL, on 12 columns, check constraints, validating document status transitions and file size ranges, a unique constraint on a composite key of user ID and document hash to prevent duplicate uploads, and foreign key constraints linking documents to users, folders, and workspace records across 4 related tables. On launch day, the platform onboarded its first enterprise client, a legal firm with 2.3 million existing documents, migrated in a bulk import that evening. The following morning, the platform opened to the client's 800 users. Write throughput under concurrent load was measured at approximately 31% of the performance benchmarks established during staging. The foreign key checks across 4 tables on every document write, combined with the unique index lookups on the composite key, were each individually modest operations. Under 800 simultaneous users generating continuous write activity, they compounded. The constraint overhead accounted for an estimated 68% of total write latency. The platform was functional, but noticeably slow. 2 weeks of performance work followed, including index restructuring, selective constraint deferral, and query plan analysis. The constraints were not wrong. The performance profile of enforcing them at scale had never been measured. This is the constraint performance problem in its typical form. Not a single constraint that is catastrophically slow, a cluster of individually reasonable constraints whose combined cost under real load exceeds what any development or staging environment revealed. Understanding why requires understanding what each constraint type actually does at the engine level. A NOT NULL check is essentially free. It is a null comparison on a value already in memory. A check constraint evaluates an expression, cheap for simple comparisons, potentially significant for complex expressions involving functions or subqueries. A unique constraint requires an index lookup, fast in isolation, but every concurrent write to the same index creates contention, and heavily written unique indexes on high cardinality columns can become serialization points under load. A foreign key constraint on insert requires a lookup in the reference table's index to confirm the referenced key exists. One additional index read per insert per foreign key. On a table with 4 foreign keys, every insert touches 4 additional indexes. At 100 writes per second, that is 400 additional index operations per second that do not appear in any single operation benchmark. There are 3 things that address this. First, measure constraint overhead explicitly before launch, not after. This means running write load tests against a production-scale dataset with the full constraint set active and comparing the results against the same tests with constraints disabled. The delta is the constraint overhead. If that overhead is acceptable, proceed. If it is not, the time to discover that is before 800 users are waiting for their documents to save, not after. Staging environments that use small datasets are not capable of revealing this. The test must be at scale. Second, understand the specific cost profile of each constraint type in your database engine. Foreign keys and unique constraints carry the most significant and most variable performance implications. For foreign keys, the direction of the lookup matters. Inserts into child tables are more expensive than deletes from parent tables in most configurations. For unique constraints, the cardinality of the indexed column and the right concurrency against it determine whether the constraint becomes a contention point. Neither of these costs is constant. Both are load-dependent. Third, where performance requirements cannot be met with all constraints active, make the trade-off deliberately rather than accidentally. Some constraints can be deferred, executed at transaction commit, rather than on each individual statement, which can significantly reduce index contention in bulk write scenarios. Some constraints can be partially relaxed at the cost of additional application-level verification. Some can be enforced asynchronously through background reconciliation jobs, rather than inline on every write. These are real trade-offs, with real implications for data integrity. The point is not that they should always be made. It is that they should be made with full knowledge of what is being exchanged, rather than discovered under production load when the options for responding are more constrained. The customs checkpoint does not disappear because the port gets busier. The inspections still happen. The manifests are still checked. The weight is still verified. The cost of that process, which was invisible when 50 containers passed through each day, becomes the dominant operational fact of the port when 5,000 do. The checkpoint was always doing that work. The volume simply made it impossible to ignore. Every constraint in your schema is doing work on every write. That work is correct, necessary, and in most cases worth doing. But it is not free. It does not scale linearly, and it does not behave the same way under 100 simultaneous users as it does under one developer running tests on a laptop. The performance profile of your constraints is not an implementation detail. It is a property of your schema that needs to be measured, understood, and planned for before the load that reveals it arrives.